And so I will welcome the first speaker, Chantal. And while she gets ready, I will tell you a bit about her. So she studied electrical engineering, which is the best subject to study because I studied the same. And she focused on projects with like a social impact. And in those projects, she used Python. Yes. And she's motivated a lot by like the potential of technology to improve life. So if you're like me and struggle when you go for shopping at Migros, for example, if you struggle to find your stuff, and you can maybe somewhat relate to how this is even worse for people that are like visually impaired. So her talk will be about improving the shopping experience of visually impaired using computer vision and machine learning and all the tools that technology has available. So yeah, please a warm welcome to Chantal. Stage is yours.
Thank you very much for the introduction. So yeah, welcome from my side as well. I'm also very pleased to welcome you to the Swiss Python Summit today. And it's really a great honor for me to open the series of presentations today and introduce you to my work on robot-assisted shopping for the visually impaired. But how did I come to focus on such a specific application of Python? As part of my master's thesis, here at the Eastern Switzerland University of Applied Science, I intensively examined how visually impaired individuals manage their daily lives, particularly grocery shopping. Topics with positive social impact have always been important to me, especially when it comes to providing disadvantaged groups with more autonomy and independence. Based on my research findings and the valuable feedback from those affected, I began working as a research assistant in the Autonomous Systems Department here at the Institute for Lab Automation and Mechatronics, after finishing my master's degree this year. The project VIRUS, which stands for Visually Impaired Robot-Assisted Shopping, was launched, and I've been leading the project ever since, working closely with a team of 5 further developers. So, let's first take a look at the relevance of the topic. Approximately 7% of the world's population is affected by visual impairments, with around 4% in Switzerland. These numbers are expected to rise due to demographic changes and an aging population. Everyday tasks, which are taken for granted by most of us, pose a constant challenge for this group. This is particularly true for essential, recurring tasks, such as grocery shopping. Now imagine what it would be like if a simple trip to the supermarket, something many of us can do without assistance, suddenly became impossible to manage independently. For visually impaired individuals, obstacles in supermarkets are everywhere, from locating products, identifying and recognizing offers, to navigating through the store. These barriers not only make shopping more difficult for this group, but also severely impact the independence and quality of life of those affected. So that's why we evaluated the need for and interest in a solution like VIRUS. We conducted a survey of 100 visually impaired and blind individuals in Switzerland and Germany. The results show that nearly 90% of respondents would welcome a robot-assisted shopping aid and see the potential for it to enable and improve their self-guided shopping experience. This is precisely where our VIRUS shopping cart comes into play. The cart enables barrier-free navigation and product identification through the use of artificial intelligence and innovative robotics. Our goal is to significantly enhance the quality of life for people with visual impairments and blindness, and to strengthen their participation in society. Now, I would like to show you how our project not only overcomes technological challenges, but also places the wishes and needs of those affected at the center. I will demonstrate how, through the use of Python, visually impaired individuals can independently detect products via hand tracking and acoustic guidance. So let us take a closer look at how the virus shopping cart can improve the shopping experience for this group. So I would like to show you a short video so that you can get an impression of how the entire system works. Since our target audience is in German-speaking regions, the video is in German, but I've added English subtitles.
Ich möchte gerne eine Milch kaufen.
Achtung! Der Wagen fährt los. Wagen stoppt. Achtung! Der Wagen fährt los. Wagen stoppt. Die Milch befindet sich rechts von Ihnen. Nach oben. Nach vorne. Nach rechts. Sie haben die Milch gefunden. Ihr Einkauf ist beendet. Vielen Dank. Achtung! Der Wagen fährt los.
So, as you just have seen, virus is not only a technological change, it is also a promise to all those who face barriers in their everyday shopping experience. Barriers that are not even noticeable for people without impairments. But how does Python now enable the functionalities of the virus shopping cart? In this talk, I will focus on basic and easily understandable Python modules that can be used for product and hand recognition as well as speech processing. These features are also the core components for the functionality of the system and are crucial for the shopping process. If we were also to cover mapping, we would far exceed the time available here. So, as shown in the video, two stereo cameras are used for product and hand recognition, which are placed at the left and right side of the cart. They scan the shelves, identify the products, and track the hand. With the headset, the hand is acoustically guided to the desired product, and the shopping list can also be communicated verbally. Foundation for product recognition is a pre-trained object detection model that enables the simultaneous real-time recognition of multiple objects by processing the entire image in a single pass. This is crucial for ensuring fast identification of products, especially when they are close together or overlapping. So first, the object detection model is loaded. The pre-trained weights are transferred to the GPU. These weights are essential as they represent the knowledge the model has acquired during training. Next, the stride size of the model is determined. The stride indicates how many pixels the model jumps over when processing an image. It determines the resolution of the prediction. The larger the stride size, the fewer details can be detected, but also the faster the processing. So the camera now captures live images, which are then prepared for the object detection model. They are resized to the required size, and the color schemes are converted. The image is normalized so that the pixel values, originally ranging from 0 to 255, are now scaled to a range between 0 and 1. This is important to ensure that the model works consistently with the values it learned during training. The preprocessed image is then fed into the model and a prediction is generated. This prediction contains several detections known as bounding boxes with their respective confidence scores. To ensure that only the best and non-overlapping bounding boxes are selected, the results are filtered based on a confidence threshold. As a result, I received the 2D coordinates of the bounding box for each detected product. So, to guide the hand precisely to the desired product, depth information is needed, in addition to the 2D coordinates of the bounding box. This information is provided by the stereo camera in form of a point cloud, which is a three-dimensional representation of the environment. In the point cloud, each pixel value of the camera is assigned an X, Y, and Z value, where the X and Y coordinates corresponds to the pixel's position in the image, and the Z value indicates the depth, meaning the distance of the object from the camera. To determine the three-dimensional position in space, the X and Y coordinates of the center of the bounding boxes of the detected product are passed into a function. This function assesses the point cloud and extracts the Z value, meaning the depth information, based on these coordinates. The combination of the 2D coordinates of the bounding boxes and the derived depth information allows for precise localization of the product in 3D space. With this data, the hand, whose position is also captured in 3D, can be guided towards the product. So the system ensures that the hand moves accurately towards the product in horizontal, vertical, and depth direction. For hand recognition, I use MediaPipe's hand landmark detector. This library enables the spatial identification and tracking of 21 hand knuckle coordinates. The advantage of using MediaPipe is that it's already optimized and has been proven in many applications. So, to enable hand navigation to the product, I use the tip of the index finger as a reference point, which is defined as landmark 8. The decision to use the tip of the index finger is based on several practical considerations. So first, the index fingertip is the preferred finger for precise interactions with most people and intuitively points to objects. In the context of navigation, using the tip of the index finger allows for precise control as it extends farthest forward during a grasping motion, making it ideal for pointing or interacting with objects in space. Based on the live image, MediaPipe detects the user's hands and returns a set of landmarks representing the positions of the 21 hand points. My Python code then iterates over these landmarks to extract the specific coordinates of the index fingertip. The relative position of landmark 8 is calculated by scaling the MediaPipe's values to the image size. The determined X and Y coordinates of the index fingertip are then used to retrieve depth information from the camera's point cloud. So, the X and Y coordinates of the index fingertip are then passed into the function that extracts the Z value. With this depth information, the spatial distance between the hand and the product is determined. This allows for precise navigation instructions, such as move further to the left or move forward, to be generated, guiding the user to the desired product. These instructions are then passed to my text-to-speech module to provide the user with auditory feedback. When the positions match, further auditory feedback is generated through the text-to-speech module, informing the user that the product has been found. For speech output, I initially relied on the eSpeak library. eSpeak is an open source and offline available speech synthesizer. It supports the German language, which is used as our target audience is currently located in the German-speaking area. One of eSpeak's key strengths lies in its easy integration and support for multiple languages with minimal memory usage, as it's based on format synthesis. This method has the advantage of producing very clear speech that can also be used at very high speed. However, the downside of this method lies in the lack that the verbal output currently sounds relatively monotonous and artificial. But since the visually impaired places a very high value on a natural and pleasant speech output, I searched for an alternative. So, unfortunately, the selection of high quality and offline available text-to-speech libraries in Python that supports the German language is very limited. To overcome this issue, I ultimately decided to use pre-recorded MP3 files. This approach has the advantage that the audio output sounds significantly more natural and fluid as it is based on human voice recordings. However, the downside of this method lies, of course, in the lack of flexibility. Each new speech output must be manually recorded and stored as an audio file. This makes the dynamic generation of text more difficult as it would be possible with a speech synthesizer. Play the MP3 files, I use the Python module playSound. The playSound function only requires the path to the MP3 file to be played, and then it plays the file directly. For the speech input of the shopping list, I searched for a model that understands the German language and is also available offline. It should also offer the possibility to transcribe inputs in real time. After a thorough evaluation, I finally chose the open source toolbox Speech Catcher. Speech Catcher is specifically optimized for the German language and offers near real-time processing. The speech input is done directly over the microphone of the headset, providing an efficient and user-friendly experience. The process of input is simple. The user states the desired quantity and the name of the product. Speech Catcher's recognition system processes this directly and adds the product to the shopping list. So originally, I had also considered using Whisper for this task. Whisper is this speech recognition model, and it's trained on a wide range of audio data. It offers also good accuracy for the German language. But ultimately, I decided on Speech Catcher because it represents a suitable alternative to Whisper and is specifically optimized for the German language and real-time transcription. Speech Catcher is based on models developed from larger teacher models like Whisper, but offers compact and efficient automatic speech recognition models that run also well on CPUs without requiring GPU support. This makes Speech Catcher ideal for my application, as it enables smooth and precise speech processing without additional hardware requirements. So, in the corresponding Python code, I use various other libraries and modules such as PyAudio for audio capture, Torch for utilizing the Speech Catcher models, and Speech Catcher for the actual transcription. The audio data from the microphone is first captured in real time and then converted into the appropriate format for the Speech Catcher model. Using PyAudio, a stream is opened that continuously captures audio data from the microphone. The speech data is recorded in small sections, and it's already been processed in parallel using a thread pool. This minimizes latency, allowing for transcription to occur almost in real time. So the data is then passed into the Speech Catcher model, which transcribes the speech. The recognized shopping list is saved and then further processed. So now that we have considered all aspects of product and hand recognition, as well as speech processing, it becomes clear how Python plays a crucial role in the technological implementation of socially relevant topics. Python's versatility and extensive library landscape make it possible to develop innovative solutions for the specific challenges of various application areas. Especially in the development of virus, Python ensures that the needs and desires of the visually impaired are placed at the forefront. To summarize, virus is not just a technical aid, but also an important contribution on how visually impaired individuals can shape their daily lives more independently in the future. Our goal is not to make the shopping process more easier for these individuals, but to fully transform it. It is particularly important to us that virus is not only a tool for shopping, but also a symbol for self-determination and independence. We are convinced that virus has the potential to improve the shopping experience for visually impaired individuals while also offering new opportunities for an even broader audience. So our shopping cart stands for a new way of shopping. Barrier-free, independent, and efficient. Virus is a step towards a more inclusive society where everyone, regardless of their physical limitations, has the freedom to participate in public life. You cannot help men permanently by doing for them what they could and should do for themselves. We do not want to take away the independence of those affected or passively support them. We want to give them the freedom to do what they can and want to do actively. But we're just at the beginning of a project that shows how the use of Python can elevate social participation to a new level. So thank you very much for your attention and interest in my project.
Where are the helpers with the microphone?
Did you do any research on whether speech output is preferred by the users versus just outputting sounds?
Sorry, the speech output?
Speech output versus just outputting sounds, like ping for forward and pong for backward or something.
Yeah, that we also evaluated in the video. We made it very basic, but in the real application, it's more text. They have more information. They want everything to know and very detailed. So it's more precise than shown in the video. That's just for simplification.
Okay, thank you.
All right. There another question? Otherwise, I would have a question as well. It's like, does the robot have a map of the store?
Yeah.
And so he doesn't know where, so he can plan like the shopping tour.
Yeah, it should plan the tour efficiency so that the blind people don't have to run through the whole store. So yeah, he knows where the products are in the map, and he has, of course, the map.
All right. Oh, there's a question over there.
Do you think?
Just continue to speak.
Okay. Do you think at some point it will be possible to run it on a mobile phone?
Yeah.
So that you can take a normal shopping cart and put your phone on it and...
Yeah, that's also what we want to do, to switch it to a phone. But the problem is when a blind people has a phone in the hand, in the other one, his stick, his blind stick, he has no hand-free for the groceries. So that's the huge problem.
All right. Yep. I don't see any more raised hands, so thank you to you.
Thank you very much.
Very much.